Hello, Luke. Welcome to lesson 92. Today we're going to be talking about uniform motion problems about equal distances. All right, so we're back to word problems here. All right, and we've been actually preparing for this lesson for a little while. They've been giving you all kinds of systems of equations to solve for, and they've been giving you, weird variables with, subscripts like, r sub s and t sub, w, or, um, you know, um, yeah, or even D. D is another common one. D sub R or something like that, right? And they've been giving you these systems of equations with these kind of strange variables, and you've been solving them. Well, that's basically been in preparation for this class today. All right, so we'll be using that. Only now we need to find those equations first, buried within a story problem, and then we can solve them using our methods that we've been using for a long time, our substitution or our elimination methods. All right, so when we talk about uniform motion problems, you see the word motion in here, okay? And that's really what we're talking about. We're talking about problems that deal with some sort of travel. There's a rate, there's, how fast you're going. That's going to play into the problem. Maybe I'll put that. The rate is, we'll say speed. All right, that's your speed. And then you have time is another component here. How long did you travel at that given rate, at that given speed? And then finally, distance, right? The distance would just be, how far you traveled, all right? These are kind of the three legs to these uniform motion problems, all right? It's like a stool. It has three legs: rate, time, and distance, okay? We'll spend most of our time in these problems trying to find rate, time, and distance and what they equal in a given story problem. Now, when we do these story problems, there is one formula that you just need to memorize, because this is a formula that really illustrates the relationship between these three legs to our stool. All right. And the formula is distance, which I'm going to call D. Distance is equal to rate times time, R times T. All right. It's a very simple formula. There's not much to it, but it's actually very, very useful. And you'll find that you can use this for a lot of problems. So again, what is this saying? This is saying that if you want to know the distance that someone has traveled, you need to take his rate, his speed, and multiply it by his time. All right? That should be very obvious, really, when you stop and think about it. If I'm traveling at, 10 miles per hour, and I travel for 10 miles per hour for 6 hours, well, then what would be the distance? The 10 miles per hour, that's my speed, that's my rate. The 6 hours, that's my time. So what's my distance? Well, my distance would be rate times time. So distance is going to equal rate times time. And what is rate times time? Rate times time is 60. Okay? This kind of looks like a fraction. It shouldn't look like a fraction. I'm just separating these two here. Okay, so we have 60 miles in this case. That's how far I would travel if I went 10 miles per hour for 6 hours. It's just as simple as that. It's 10 times 6. Distance equals rate times time. Write that in your notebook and don't forget it. Hugely important. Distance equals rate times time. Okay, so with that being said, let's dive into this here. And I think the best way to do it is just to basically do a problem. So here they have a word problem. And up here, I've actually kind of written out the steps that we need to follow when we do these uniform motion problems. All right, so there are really 6 steps. And you should really take a moment here and write this down in your notebook so that you can refer back to it when you're doing these problems. As you do these problems, eventually this should all become second nature to you. But for right now, Obviously, it's not. So I want you to write this down in your notebook so that you can study it and you can look at it when you're doing your exercises. So pause the video and let's get that done first. All right, so let's go ahead and start working on this problem, and we'll just do it step by step based on these steps that I've laid out for you. So the first thing is to draw a picture illustrating what is happening in the problem, particularly regarding the distance. All right, so the book recommends this. There are other approaches that you could take on this, and as you kind of get used to these problems, maybe you'll find it easier to take a different approach. But I think this is a good place to start. What we're going to concentrate on is the distance within these problems. Okay, that's what we're looking for. So again, the first step is to draw a picture illustrating what's happening in the problem regarding distance. Okay, so let's draw a picture. On Tuesday, the express train made the trip in 12 hours. So distance is really referring to the trip. The trip is the distance, right? Now, it doesn't tell us how long that distance is. It just tells us that there was a trip, and that was the distance. All right, so what we're going to do is we're going to say, okay, the trip begins here, and we'll say it ends here. All right, this is the trip. There's my picture of the trip. Okay, and this we're going to call it the distance sub E. All right, D sub E, representing the distance of the express train. That's where the E came from. All right, for express. So we have the distance of the express train. There it is. Now let's talk about another distance, because the express train isn't the only thing we're talking about. We're also talking about a freight train. And what do we know about the freight train? Well, the freight train also made a trip. So it also has a distance. Now what's key here to recognize, I'm going to circle this in red so that you see how important this is. The key word here is the freight train made the same trip. It's the same trip, all right? And if it's the same trip, then it's the same distance, right? So the freight train starts at the same spot, right? And it goes to the same place. So it has the same distance. So this is the distance of the freight train. Okay? So this is crucial right here, recognizing that the two trips are the same. And once we draw this picture and we say, look at this, the two trips are in fact the same, they have the same length, well, then we can set this up in terms of an equation. What equation could we get out of this for our distances? Look at it closely. What could you say is the equation? Well, the equation would be the distance of the express train is equal to the distance of the freight train, right? There we go. That's an equation. And it's true. Those two distances are the same. So bingo, we have one equation. This is kind of the starting point equation that we will use in these problems. So again, we're kind of going to approach these the same way every time. Hopefully that'll make it easier for you. So we draw a picture of the distance, and then we set that picture into an equation form like this. All right. So that is step number 1. We drew the picture. And step number 2, we expressed the distance, the d's, as an equation. All right. Now what's step number 3? We recall the equation distance equals rate times time. D equals r times t. And express the equation from step 2 in terms of r times t. Okay, so that may sound a little confusing right there, but let's step it out. I think you'll find it's not as bad as that might sound. So we remember that distance equals rate times time. Remember I told you this is a super important equation to remember? All right, so if we pick one of these distances, let's say we want to talk about the distance of the express train. Okay, so the distance of the express train. What would we say? The distance of the express train is going to equal the rate of the express train times the time of the express train, right? I think you can see that. We're just taking the generic D equals R times T and applying it to this particular problem by replacing the D's and the R's and the T's with the D's and R's and T's for the express train, okay? In other words, we put a sub E underneath these. So what about the d sub f, the distance of the freight train? Well, we could also write that in terms of an equation. The distance of the freight train would be equal to the rate of the freight train times the time of the freight train. Right? Okay, because of that wonderful equation. All right. Now, the beauty here is we now have two more equations, and we can actually substitute in for this blue equation down here, our distance equation. All right. So we can see that d sub e is equal to r sub e times t sub e. So we can go down to our d sub e here and replace that with r sub e times t sub e. Okay. See how that works? Make sure you see that. And then we can replace the d sub f in the same way. That can be replaced with r sub f times t sub f. Okay? Excellent. Now you might be saying, but yeah, Jim, this is not helping me. We went from one variable here to two variables, and then from one variable here to two variables here. Well, just hold your horses and see how this works out, because in fact, this equation will be pretty useful. All right. So this equation has become this one. This one has become this one. Okay. Okay. So now the next step, that is, well, we finished this one here. We expressed the distance equation in terms of r and t, right? There's no more d's in here. It's all r's and t's. That's step 3. Now we need to go back to the story problem, because now we need to pull from the story problem information regarding rates and times. So what else have they told us here? So let's start pulling things from this. So we say on Tuesday, the express train made the trip in 12 hours. Well, what's 12 hours? What is that? Maybe I'll go to a different color here since we're in a different step. What's the 12 hours? Well, that's time, right? And it's whose time? It's the express train's time. So we can say that the t, representing time, sub e, so the time of the express train, is equal to 12 hours, right? T sub e is going to be equal to 12. They tell us that. So that's one bit of information. So let's put that over here. So we're trying to build a system of equations here. So maybe we will, let's see, maybe we'll just do this. So this is our first equation. Remember, that came from this blue one. And now we just found another equation in the story problem. We found that t sub e is equal to 12. So we're up to 2 equations. Okay. And remember what I've said before. You always need the same number of equations as variables in order to solve it. So right here, you could say we have 4 different variables, r sub e, t sub e, r sub f, t sub f. 4 different variables. So in order to solve this equation, we need 4 equations in our system. Okay, and every time we add a new variable, we need a new equation for that. So this second equation, we have another variable, but it's also in this first one. So we're not really adding a new variable. We're just repeating a used one already. So we still only have this in 4 variables, but now we're up to 2 equations. So that's great. We're up to 2. We need 4 though. All right, so let's keep going. On Wednesday, the freight train made the same trip in 16 hours. So again, we have an indication of time. Okay, whose time is it? Well, this is time again. So whose time is it? Well, it's the freight train's time. And what is it? The freight train's time is 16 hours. So look at that. We have another equation. We can throw that into our list. T sub f is equal to 16. So we're up to 3 equations. Notice we did not add another variable. T sub f is already in our original equation here. So that's great. We need one more equation to make this system solvable. All right. So what else do we have? Find the rate of each train if the rate of the freight train was, here we go. So the rate of the freight train was 15 kilometers per hour less than the rate of the express train. So here we have one of those kind of confusing equations that deals with, less than. Remember, we've had these before. So what are they saying? They're saying the rate, right? So the rate is the r. Okay? Remember our three variables, d, t, and r. So the rate, and what are we talking about here? We're talking about the rate of the freight train. So we're going to call that rate sub f. That was 15 kilometers per hour less than the rate of the express train. Remember, rate is just kind of speed, right? It's an averaged speed. So the rate of the express train. So which one has more? I guess that might be the place to start. If we say, okay, the rate of the freight train, let's just begin by saying it's, it's the rate of the express train. Okay. But they're not equal. One of them is going faster. Which one is going faster? Well, it says the rate of the freight train was 15 kilometers per hour less than the rate of the express train. So the rate of the express train was going faster. Okay? This is where you have to be really careful that you don't mess up which one's going faster. The rate of the freight train was 15 kilometers per hour less. Okay? So what do we have to do? We need to take the rate of the freight train, and we need to add to it 15. Because if we add 15 kilometers per hour to the freight train, that will equalize the freight train and the express train's rates. That'll make them equal. Okay? Another way to think of this is the rate of the express train is all of the rate of the freight train. It's all of his rate plus 15 more kilometers per hour. Okay? That's why the rate of the express train is faster. Okay, so make sure you can see how you get this problem. This is, again, as always, these less thans, more thans part of the problem. That's always going to be the hardest part. So really make sure your head is screwed on straight when you're figuring this part out. All right? All right, well, that is a fourth equation. And again, it's in rate sub f, rate sub e, both of which are in our original equation. So we're not adding any new variables. However, we are adding a new equation, which means we are set to go, right? Because we have four equations now with four variables. We have a system that's solvable. Okay? So now we can go ahead and solve this. All right? And the first thing that you could do is say, okay, so this first equation is the one we're really aiming at. It's kind of the key equation to the whole thing. We can recognize that t sub e, well, this one's already been solved, right? That one's already solved. We can plug that right in to this t sub e. The t sub f, that's already been solved. We can plug that right into the t sub f. All right, so let's do that and see what that gives us. Maybe I'll go back to this color. So the rate sub e, we're going to have rate of e times t of e, which we know is 12. So I'm going to write it over here. 12 times rate sub e is equal to rate sub f. We don't know what that is, but we do know that t sub f is 16. So it's going to be 16 times rate sub f. Okay? Now we need to decide how we could plug something in for this rate sub f or this rate sub f, or e, rate sub e or rate sub f. Okay, well, let's look at this last equation. We can recognize that this one has been solved for the r sub e. Okay, so we can plug this into the r sub e. So that's going to give us 12 times r sub e, which is the same thing as r sub f plus 15 equals 16r sub f. And now we can multiply this out. We're going to end up with 12r sub f. 12 times 15, might have to do this off on the side. 12 times 15 is going to be 180. So we have 180 is equal to 16r sub f. We can move the 16r sub f, well, actually I'll move the 12r sub f over to the other side. And by subtraction, that's going to give us 4r sub f equals 180. And 4 can go on to 180, what, 45 times. So r sub f is equal to 45. So the rate of the freight train is 45. Okay. The rate of the express, we said that was over here, was 15 plus the rate of the freight train. So the rate of the express is going to be the 45 plus the 15. I'm just plugging it into this equation over here. 45 plus 15 is 60. So the rate of the express train is 60. All right. And if I wanted to put units, I would say that it's, 60 kilometers per hour. So kilometers per hour. Okay. And there you go. That's all they wanted to know. They wanted to know the rates. Find the rate of each train. So there you have it. We didn't even need to find the distance. They didn't ask for the distance. Now, we certainly could now plug in R sub E and R sub F, into this equation right here, R sub E and R sub F, and we could, solve for these two distances if we wanted to. Okay. All right. So hopefully that kind of made sense. You can see there are quite a few steps here that we need to do. And by the way, I wasn't checking those off, but we did them over here. So we pulled from the story problem information regarding rates and times. And then we checked to make sure that we had the same number of equations. And then we just solved the system of equations. In this case, we kind of use substitution to solve for this system. All right. Very good. So let's try another one here. I think this is just going to have to take some practice. Maybe I'll just throw up here of steps. All right. So tell you what, why don't you pause the video? Try this one on your own first. See how well you do. And if you get it, great. If not, we'll do it together and iron out any wrinkles that you might have. All right, so it says the members of the girls' club hiked to Lake Tenkiller, interesting, at 2 miles per hour. By the way, I got these story problems directly from the textbook. So if you're wondering where these came from, I didn't write them myself. They are from your textbook. So Mr. Ali gave them a ride back home at 12 miles per hour. Find their hiking time if it was 5 hours longer than their riding time. How far was it to Lake Tenkiller? So here they're actually asking for two things. They want to know the hiking time, but then they also want to know how far was it. They want to know the distance. All right, so we have a little more work maybe to do on this one. So once again, though, let's break it down. We want to draw a picture. So here's our starting point. And the members of the girls' club hiked to Lake Tenkiller at 2 miles per hour. So wherever they started, they hiked. Let's say they started at school, and they hiked up to Lake Tenkiller. Boom, boom, boom. Here's Lake Tenkiller. And this is their distance. So this would be the distance of the, well, let's see here. Let's see. The member of the girl hiked. I'm going to call this distance, I guess maybe distance sub t, the distance 2, if that makes sense. Now, one thing to point out here is maybe a little bit of direction. So they started here, and then they went this way. Okay, so they went this way to their destination. So we'll call that the distance 2. Okay. Now, once there, Mr. Ali gave them a ride back home at 12 miles per hour. So once they were there, they then started at the lake, and they went this direction, back home. Okay, they went this way. So this I'll call the distance from. So we go the distance to the lake and then the distance from the lake. Okay, so d sub t, d sub f. Now, the question here is, how can we compare these distances? Just like last time, we need to somehow write these distances into an equation. So what could you say about these distances? They're equal, right? The distance to the lake is equal to the distance from the lake. We're going different directions, but the distance that we travel is the same. So it just looks a little bit different from the last one because of that to and from business. But if you really stop and look at the distances, they are the same, just like the last one was. All right. So now these two distances remembering our formula, remember this wonderful formula, distance equals rate times time, we will now break these down into R's and T's, right? So we did this, we drew the picture. Now we're going to express the distances as an equation. Well, actually, we did that. Now we're going to recall the equation d equals r times t and write it in terms of r and t. So the distance of t is going to be equal to r sub t times the time sub t. Okay, and then the distance of f is going to be equal to r sub f times sub f. There we go. That is our first equation. And remember, we're trying to get, in this case, we have 4 variables, so we want 4 equations. Okay, so there's our first one. Now, we did this. We're on to step 4. We need to pull out more information from the problem. So the members of the girls' club hiked to Lake Tenkiller at 2 miles per hour. What is 2 miles per hour? Remember, the R, the T, and the D. It's got to be one of those. It's not distance. It's 2 miles per hour. It's not time, it's rate, right? That's what that is. So the rate, and I'm going to call this the rate to, right? Because we're going to the lake. The rate to the lake, the R sub T, is equal to 2. It's 2 miles per hour. All right. Now, Mr. Ali gave them a ride back home at 12 miles per hour. So we have another miles per hour. This is another rate. Right? But it's going the other direction now. Now we're going this way. We're going back home 12 miles per hour. So this is going to be the rate of F. Rate from the lake is 12. Okay, so we're up to 3 equations. Looking good. Now it says find their hiking time if it was 5 hours longer than their riding time. So now we're dealing with time, right? So we're dealing with T's. So their hiking time. Well, the hiking time was the hike to the lake. So we're going to call that T sub T, the time to the lake. Okay? And then if we go the other time, the riding time, that's the time from the lake. So the hiking time was 5 hours longer than the riding time. Okay, well, that would mean that the riding time, or if you want to do it the other way, the from time, from the lake, is going to be 5 hours less than the time to the lake. Okay, so this again to make sure you have your head screwed on. So the time to the lake, the time that it took them to the lake, is going to equal the time that it took them to come from the lake plus an additional 5 hours. Okay, make sure that this makes sense to you. The time to the lake, that would be this distance. This distance here, the time to the lake. This time, because they were walking, it was going to be a lot slower than when they went back home. That's faster. So this time to the lake is going to equal whatever time it took them to come back from the lake, but then we have to add another 5 hours to make this time longer, right? Hopefully that made sense. So the equation then is time sub t is equal to time sub f plus 5. Okay, there we go. We have our 4 equations now. Now we can go ahead and solve. So we begin by, going to this first equation again and just start plugging things in. R sub t, we do know what that is. R sub t is equal to 2. So we can replace this with a 2, right? So that becomes 2 times t sub t. We don't know what t sub t is. Or actually, we do know what t sub t is. What am I saying? We do know that. That t sub t is right here. It's equal to this. So we can replace the t sub t with t sub f plus 5. All right. And then we have our equal sign. R sub f, we know what that is. It's a 12. So we can replace that. And then t sub f, we don't know what that is. So we leave that just the way it is. Okay, now we can multiply things through. So we end up with 2 t sub f plus 10 equals 12 t sub f. If I subtract the 2 t sub f from both sides, I'm going to end up with 10 is equal to 10 t sub f. Divide both sides by 10, and I'm going to end up with 1 is equal to t sub f. So the time from the lake is equal to 1 hour. Okay? And what do they want to know? They want to know, find their hiking time. And the hiking time was the time to the lake, right? So the time from the lake was 1 hour. That's not what we want. We want the time to the lake because that was the hiking time. So how do we find that? Well, we need to plug this 1 into this equation. So time to the lake is going to be equal to time from the lake plus 5, which is 6. So the time to the lake is 6 hours. 6 hours to the lake. Or you might say that's their hiking time. Right? There you go. 6 hours. All right. Now, how far was it to the lake? Well, we need to know one of these distances. Okay? So, you can decide which one you want, I guess. What do we do to find distance? We go distance equals rate times time. So the distance, and it doesn't really matter which one you pick because the distance is going to be the same, but we'll just say the distance to the lake is equal to the rate to the lake times the time to the lake. All right? And we know that the rate to the lake was 2 miles per hour. Right here. Rate to the lake is 2 miles per hour. Time to the lake, we just solved for that. The time to the lake is 6 hours. So we're going to multiply that by 6. And that would mean that the distance to the lake is, maybe I should put some units here, 12 miles. That would be the distance to the lake. So it took them 6 hours to get there, and they traveled 12 miles. And that answers all the questions that they want to know. All right? So hopefully that maybe made a little more sense to you than the last problem. Let's try one more and make sure that you've got this down pat. All right. So once again, we'll maybe just throw this on here so that we can step our way through things. Pause the video again and try this one on your own, and then we'll do it together. All right, so let's see how you did. So once again, we have to draw a picture, but let's first read the problem. Durant drove to the oasis in 2 hours, and Maddel walked to the oasis in 10 hours. How far is it to the oasis if Durant drove 16 miles per hour faster than Maddel walked? All right, so we have a spot where Durant started, and then he drove to the oasis. That's the distance. Maybe we'll call this one D sub D, maybe, for distance drove. Okay. And then Durant, Maddel walked to the oasis. But we're assuming that they started at the same place. They don't say that explicitly, actually, but let's just assume that they do. So they started at the same place, and now Maddel walked to the oasis. So we'll call this the distance sub W for distance walked. All right. And again, the key thing to recognize here is that the distances are the same. They both started in the same place. They both ended in the same place. So if you want to draw your arrows in, he walked from here to here, and then Maddel walked from here to here. Okay? So once again, what can we say about these two distances? We can say that the distance that he drove is equal to the distance that he walked. Okay? So the d sub d is equal to d sub w. That's step number 1 and step number 2 taken care of. Step number 3 is writing this in terms of r and t. So distance sub d is going to be equal to the rate sub d times the time sub d, right? And the distance sub w is going to be the rate sub w times the time sub w. Okay, so there we go. There's our first of 4 equations. Now we need to pull things from the story problem to get some more information. So Durant drove to the oasis in 2 hours. What's 2 hours? That's time. So we have the time of driving, because this is, where he drove. So the time sub d is equal to 2. Okay? And Matt'll walk to the oasis. Now we have the, in 10 hours. In 10 hours. So we have the time of the walking is equal to 10. Okay? And then, how far is it to the oasis if Durant drove 16 miles per hour faster than Medell walked? So if we think about Medell's walking speed, again, this is rates we're talking now. So the rate of Medell's walking, R sub W, the rate of, the rate of the walking speed. So the rate of the walker is going to be equal to, we'll do it the other way around. Let's do the rate of the driver. The rate of the driver is going to be equal to the rate of the walker. Okay, so he's going as fast as the walker is, and in addition, he's going 16 miles per hour faster still. So the rate of the driver is the rate of the walker plus an additional 16. That's what this is saying. Okay, Durant, who's the driver, he's 16 miles per hour faster than Medell walked. So we need to add 16 to Medell's walking to get that to be equal to the driving. Okay? All right, again, that's the trickiest equation, I think, right there. All right, so once we have all 4 of these, now it's just a matter of solving it. This should be the easy part. All right, we just start substituting in. What do we know about R sub D? Well, R sub D is actually equal to this. So we can plug that in, R sub W plus 16. But then we're multiplying that by T sub W. So we have to take this whole expression, and we're multiplying that by T sub W, or T sub D, excuse me, and T sub D is equal to 2. So we'll set that out in front. And then that's equal to R sub W, which we don't know, times T sub W, which we do know, that's 10. All right, so now we just need to do some multiplying here, and we end up with 2R sub W plus 32 is equal to 10R sub W. We can subtract the 2R sub W from both sides and get 8R sub W. Then we can divide both sides by 8, and we end up with R sub W is equal to 4. And what would that be? That's the rate. So it's really, let's maybe write that in here. The rate is going to be 4. What are we doing here? It's hours and it's miles. So it's miles per hour. Okay. Whoops. Miles, not meters. Per hour, if you can read my handwriting there. All right. So there you go. So there is the rate of the walking. Now, what do they want to know? They want to know how far is it to the oasis. That's their big question, is how far. So they want to know distance. They want to know what one of these distances are. And they're both going to be the same, so it doesn't matter which one we solve for. We do know that the rate of the walker was 4 miles per hour. We do know that the time of the walker was 10 miles per hour. And we do know, because we've memorized this equation now, that if we want to know distance of the walker, we have to take the rate of the walker, the rate of the walker times the time of the walker, right? Rate of the walker times the time of the walker. And we know that the distance of the walker then is going to be the rate of the walker, which is 4, times the time, which is 10. So if we multiply that out, the distance of the walker is 40 miles. And if that's the distance of the walker, it's also the distance of the driver, because the distance is the same. So there you have it. The Durant drove, let's see, how far is it to the oasis? It's 40 miles to the oasis. Okay? All right, so hopefully that makes sense to you. Some of this you just need to practice it. When I'm doing it, maybe it looks a little bit easy because I know what I'm doing. But you'll find that after doing a couple of these, you should start to kind of get into a rhythm, and they really aren't that bad. Solving them is easy. You've been doing this for a while now. It's just setting up those 4 equations that you have to master. Okay? All right, so we will stop here for today, and I will see you tomorrow.